Nuclear energy. It's one of the most powerful and maybe one of the most controversial energy sources humanity has ever gotten its hands on. It promises this almost limitless power from just a tiny amount of material, but, of course, it also comes with some pretty huge risks. So, how does it actually work? Well, let's unlock the secrets hidden deep inside the atom.
So it really all starts with this one question, right? How on earth can something as small as a little ceramic fuel pellet hold the same amount of energy as a literal ton of coal? I mean, think about that. The answer isn't in chemistry. It's not like we're just burning something. No, this goes way, way deeper, right into the atom itself.
And this image really just says it all, doesn't it? On one side, you've got that single uranium pellet. After it's been processed, that one tiny thing has the energy equivalent of an entire ton of coal. It's an energy density that is almost impossible to wrap your head around. To even begin to understand how that's possible, we have to go subatomic.
All right, so let's get into the science behind this incredible power. And listen, this isn't just going to be some dry physics lesson. This is the fundamental secret that makes all of nuclear energy possible. And it all kicks off with this strange little quirk in how atoms are built. Okay, so think about the nucleus of an atom. The core. It's made of protons and neutrons. Now, logically, you would think that the total weight of that nucleus is just, well, the weight of all its individual parts added together. Simple enough, right? But if you actually do the math, you find something that just doesn't add up.
And this brings us to this really fascinating idea called mass defect. What it means is that the individual parts of a nucleus, all the protons and neutrons weighed separately, actually weigh a tiny bit more than they do when they're all stuck together in the nucleus. The whole is literally lighter than the sum of its parts.
Which, of course, leads to the big question. Where did that mass go? I mean, it can't just vanish into thin air, can it? And this right here, this is the heart of the matter. This is the key to unlocking all that incredible energy.
So that missing mass, it was converted into a tremendous amount of energy. And this is perfectly described by Einstein's super famous equation, E=mc². We call this energy binding energy. And it's basically the cosmic glue that holds the entire nucleus together. And if you can break that bond, you release that energy.
So we know there's a ton of energy locked away in there. But how do we get it out in a controlled, useful way? Well, the answer is a process that sounds like it's straight out of science fiction. A chain reaction. The key process here is called fission, and it's pretty much exactly what it sounds like. We are intentionally splitting the nucleus of an atom. And when that split happens, that binding energy we were just talking about is released, mostly in the form of heat, a lot of heat.
So how does this whole fission thing build on itself? Well, a chain reaction is kind of like a set of atomic dominoes. It all starts when one free neutron hits a uranium nucleus, causing it to split. Now that split releases a huge amount of energy, but, and this is the critical part, it also releases 2 or 3 more neutrons. Those new neutrons then fly off and hit other uranium nuclei, causing them to split, and on it goes. It becomes a self-sustaining reaction.
But here's the catch. You can't just use any old chunk of uranium. This chain reaction really only works with a specific version, or isotope, of uranium called uranium-235. And the problem is, it's incredibly rare. It makes up less than 1% of all the natural uranium we dig out of the ground. That's why the ore has to be refined in this complex process called enrichment, which boosts the concentration of U-235 up to a level that we can actually use.
Okay, so we've got the physics down and we've got the fuel. Now we need the machine. How do you safely contain and control an atomic chain reaction to generate electricity? Well, that's the job of the nuclear reactor.
So this gives you a simplified look at a reactor core. And yeah, it looks pretty complex, but it's really a very, very finely tuned machine with just a few key parts. And each one has a very specific job to do when it comes to managing that fission process. First up, you've got the fuel rods. This is where all the action happens. Remember those little ceramic pellets of enriched uranium? They're stacked into these long metal tubes, and bundles of these rods are then submerged in the reactor core, all ready to kick off that fission process. Next, we have something called the moderator, and this is absolutely crucial because the neutrons that get released during fission are actually moving way too fast to be reliably captured by other uranium atoms. The moderator, which is usually just water, acts like a brake. It slows those neutrons down to the perfect speed to keep the chain reaction going efficiently. So if the moderator helps keep things going, the control rods are the brakes.
They're made of materials that are just fantastic at absorbing neutrons. By lowering them down into the core, they basically soak up neutrons and slow the reaction down. You raise them up, and the reaction speeds up. This is the main way operators control the reactor's power output.
So we've gone through all this trouble to harness a controlled nuclear reaction to produce an incredible amount of heat. But how does that become the electricity that powers our homes? Well, as you can see from these steps, the rest of the process is actually pretty old school. At its heart, a nuclear power plant is just a very, very high-tech way to boil water.
And here you can see the whole system in action. The heat from the reactor boils water, which creates high-pressure steam. That steam then spins a giant turbine, which is connected to a generator, and that's what makes the electricity. Finally, that steam is cooled back down into water, usually in those big, iconic cooling towers, and it gets sent right back to the start of the cycle to do it all over again.
Now that we get how it works, we've got to talk about the bigger picture. Because nuclear power isn't just a science experiment, right? It's a real-world energy source with some very significant trade-offs that involve its power, its environmental impact, and its cost. So let's just look at the data, side by side. To make the same amount of power, a nuclear plant needs about 30 tons of uranium a year. A coal plant? It needs up to 3 million tons of coal. And while it's running, the nuclear plant produces 0 CO2. The coal plant, on the other hand, pumps out 7 million tons. But here's the trade-off. The nuclear plant produces about 250 tons of highly radioactive waste that we have to figure out how to manage for thousands of years. So it really all comes down to this balancing act. On the one hand, the advantages are pretty clear. You get immense, reliable, round-the-clock power with 0 carbon emissions. But on the other hand, the disadvantages are just as serious. You have astronomical construction costs, the unsolved problem of long-term radioactive waste, and of course, the potential for catastrophic accidents.
And that challenge doesn't just end when the fuel is used up. This chart here shows the whole nuclear fuel cycle, from mining and enriching the uranium to using it in the reactor, and then, finally, to its disposal in a long-term storage facility. Safely managing this material is an incredibly complex process that lasts for literally thousands of years. And that long-term waste is probably the single biggest challenge for this technology.
So, in the end, we're left with this fundamental dilemma. Tucked away inside the atom is a clean, reliable, and almost unimaginably powerful source of energy. But getting to it comes with these profound risks and very heavy responsibilities. There are no easy answers here, which leaves us all with a final question to think about. Faced with this choice, how do we power our future?